That's not the way I'm supposed to be doing it. There we go. Yeah. So this is our board of what's happening this week. That's not helping. Oh, it's tipped up too high, maybe. There we go. Okay, so what's happening this week, the 27th to May 1st? Coulomb's Law Pet Lab, that was due on Monday. And again, I'm still learning about this remote learning thing, so I'm beginning to label what the assignment is, what type of assignment it is, so that you can decide, well, I don't have time to do all the assignments, let me do these 3. So this is a lab, you should do that one. That was due Monday. Suggested. So this counts as an assignment. It doesn't count against you if it says suggested, if you do not do it. And that was the study guide. Today is the quiz. It's a quiz. So that has as much weight as performance task. So you need to do that. Ohm's Law, Phet Sim due Thursday. That counts as a lab also. Labs count more than assignments. So I want you to do that. And then on Friday is the extra credit. And that's a game. I got a response from one student saying that was really fun. But it's extra credit. If you haven't done all the week's work, you're not getting the extra credit. So don't bother. Okay? Do all the week's work, and then you're eligible for extra credit. That's what the extra means. So today, let's go ahead and talk about, we talked a little bit about current last time. I'm going to try to light a bulb today. And again, it worked this morning, so who knows what's going to happen now. And then Friday, I'll be talking about series and parallel circuits. So today, how to light a light bulb, and Ohm's Law, and some symbols that we use. And if we have time, I'll mention power as well. So let's start with the bulb. Let me move this out of the way and get the table that I have. There we go. You can kind of see the table. I don't know how clear anything is on that, but all of the parts are really small, so I apologize for that. Here's a battery. So one thing that I do want to talk about a battery, this is your voltage source. So this, and it doesn't say on it. Oh, yes, it does. It has 2 different sides, 2 different ends on the battery. This one has a positive. So this is the positive end, and it's sticking out. So there's a little extra on this end. And this is the negative. Sometimes the batteries have a little indentation there, so there's a little bit less. So that's your negative side. What else does the battery tell us? The actual battery. I'm trying to find it on here. Oh, this is really small. It's right up here, 1.5 volts. Let me see if it's bigger on this one that I have here. No, it really isn't any bigger. But on this one, this is our AA. It's a smaller battery, but it has the same voltage, 1.5 volts. So most of our batteries that look like this, they have a flat end and one end that's sticking out. it are 1.5 volts. You know, we have the rectangular batteries. I'll try to remember to grab one for next time that are 9 volts. And then, of course, the outlet that we plug into is different. Now, the only bulb that I have at home, I didn't pick any up when I was at school a couple of weeks ago, is a Christmas light bulb. So here, coming out of the bulb, we have a wire that comes out on one side and a wire that comes out on the other side. Anyone that has used Christmas lights before, you know that if one of them goes out, a whole section of the string goes out. We'll talk about that on Friday, why that happens. But you know, it's these metal wires here that when you're sticking another one in, you have to be sure that those are in direct contact with the inside of the bulb, with the metal on the inside of the bulb. So I have my battery, I have my bulb, so I want to light it. So I'm going to touch one of those metal pieces to the battery, and nothing happens yet. So let's use the wire. If I touch one end of the wire, and this wire is copper wire, and I cleaned the ends off a little bit so that the coating that's on the outside, so that's your insulator that's on the outside of the wire, is sanded off of the ends here. So I'll touch one end here, and so far I haven't made the bulb light. Let me touch it in the same place that the other side of the battery is touching. So it doesn't light there either. I did get a little bit of a burn there though, because I did actually have complete circuit at this end. So let's try again. Maybe if I touch the other side of the bulb, and I don't know if you can see that. Can you see that it's lit up? There it's lit, there it's not. There, oops, it moved. Oops, dropped it. So that's how we get a complete circuit and we get the bulb to light. I can try one more time if you want, but we did make it happen there. So that's better than what happened on Monday, or last Monday rather. No, I'm not going to do that now. So one thing that I do want to say, we have to have a complete loop in order to have our circuit. When we had one end of the wire touching, but the other end was elsewhere, we didn't have a complete loop. When I had one side of the bulb touching one side of the battery and the other side of the bulb touching the wire, that's when we got it to light. Now, according to convention, the circuit always flows from positive to negative. That's convention. We use convention because it was Benjamin Franklin that kind of came up with this idea. You know, he had gone out and decided, wait a minute, I think that if I take my kite out in the rain, I can get lightning to strike it. And sure enough, he was able to show that lightning was going to strike that. So he came up with original ideas about electricity, and he decided on assigning one side a positive and the other side a negative, and that when the current flows, it's going from positive to negative. He didn't know anything about protons and electrons. That came much later. So he said that the flow of charge is going from positive to negative. Later, we found out about electrons, and we now know that it's actually the electrons that do the moving. It's not the positive protons, it's the electrons that do the moving. but we stick to convention because as far as our calculations or wiring go, it really doesn't make a difference whether the electrons are going from the negative side of the battery to the positive, or if the current is flowing from positive to negative. So we stick with convention. That's just to make everything easier for you to understand why we're saying that. So now let's talk about an open loop and a closed loop. Let me go ahead and move this table out of the way again. And I'll bring this back so that I can. I'm sorry, I skipped this part about a light bulb. So there are other types of light bulbs that, and this is a kind that has been more common in homes. But now we're kind of going more towards LEDs because they're more efficient than this type of a bulb. But let's talk about getting a complete circuit with the light bulb. So when we look at a bulb, it seems like, oh, okay, so we have metal on both sides of the bulb. You must have to touch one wire to one side and the other wire to the other side. But this metal is all conducting. So if you touch one on one side and one on the other, it's going to short out because that metal conducts those electrons. It doesn't matter if you're over on this side or this side, the charge is the same in that metal everywhere. The trick is that at the bottom of the bulb, we have another piece of metal, and that's right at the tip of the bulb. It sticks out a little bit. And so what we actually have to do is connect one side of our circuit to the bottom of the bulb and one side of the circuit to the side of the bulb. And then that way, it's a little bit far away. Nope, too close. Okay, that way the current coming in the wire goes to this wire here. That wire goes up to the filament, and I'm sure you've seen a filament in a bulb that has burned out. This one has not burned out, so you can't really see it. But the filament, that's that coil of wire that's in there, and that's what lights up in your light bulb. It's a different material than these wires that are conducting the current from the input to the output. So this is the material that lights up, that heats up and gives off light. And then the circuit continues out the side of the bulb so that we have the same way as we did with the battery. We have an input and an output. So it's going from positive to negative. So that means that there is a 1.5 volt difference between one side of this battery to the other. And of course, I can't use this to light up an electric light bulb because I need 120 volts to do that. This is 1.5 volts. So truly, in order to have a circuit, we need to have a potential difference. We need to have a difference in the voltage from one side of the circuit to the other. So just like we talked about on Monday, that with water, your water is, let's say it's flowing along a river. It comes to a waterfall and then spills over the waterfall. So this is our water. Oh, I love my art. It's absolutely horrible. Sorry If I was in the classroom, I would pull up something on the computer for you and show you. And then your water ends up at the bottom where it has a lower potential energy than it does up here. So this is our high potential. At the top, remember, potential energy is dependent on the height. So the higher the water is, the higher the potential energy is. And then this is your low potential. Now, if all this water was at the same height, is the water going to flow? So no, if the water has the same potential energy everywhere, then it's not going to go anywhere. It's going to stay in one place. We do not have a flow of water if the potential energy is the same everywhere. It's the same thing with current, electric current. It does not flow if there is not a potential difference. So it's the job of this battery to maintain a potential difference. It's as if this battery is a pump, and I'll talk a little bit more about that on Friday. But the pump, this battery, is maintaining a potential difference in the voltage from one end of the battery to the other, from the negative side to the positive side. So in order to have our circuit, we need to have a potential difference, and we also need to have a complete loop. Let me see, I have one more board that's not written on. I can start erasing boards too. So here we go. Let's go ahead and take a look at a circuit. We're going to start with the battery. So the symbol for a battery is a short line followed by the longer line. Now let's go ahead and say that we're lighting up a light bulb. I'm going to use the symbol for a resistor, a zigzag line. That's a symbol for your resistor. And these straight lines are your wire. This way, I have a complete loop. You can see that we start out at the battery. We go through the wire to the resistor, through the resistor, maybe a bulb, to the wire, and back to where we started from. There's a complete loop. Now, if I decide to put a switch in here, and there are different ways of drawing switches. Let me see, what's this one? So we can put a circle here. If we put a switch in here and the switch is open, then that would be the off position, because you can see we have broken this loop. This is an open circuit. We think of things when they're open, that's the good thing. But really, we need to have that switch closed in order to make the bulb light. So it's important to remember that closed is what we want for a circuit, because that completes the path. This one, the switch is closed. This one, the switch is open. We have no light. This one, the switch is closed. We have a light. This is going to light up. So let's go ahead and give some units and some labels to some of these things that we have happening here. So potential difference is our voltage. And the units of voltage are volts. So I'm going to put that in parentheses. All right, potential difference, voltage, V. Let's say that we have 9 volts here. Now, let's look at what else we have happening in this circuit. We have a resistor. Let's say this is a 1 ohm resistor. I want to talk a little bit more about resistors. The units are ohms. The letter that we use for resistor is R, but the units are a Greek letter, ohm. It's like a horseshoe. So resistance, let's talk a little bit about resistance. If we were all in the classroom, we have 30 people or so in the classroom. If we had to get out in a hurry, maybe there's a fire drill or something. If we only have one door that we can get out, it's going to be slow going through the room, and everybody having to file out, single file out one door. Now, what happens if we open up a second door? We're going to get out faster, right? We have two doors in our classroom at Pitt. So we're going to be able to get out faster if we have 2 doors open. That means there's less resistance because we opened up another door. Another way of looking at it would be at a toll booth. So you're driving along, you come to that toll. What happens? You always have to slow down because it takes time to get through the toll. If you only have one toll booth open, there's a lot of resistance, and so that slows you down. That's like slowing the current, slowing the traffic down. We're slowing the current down. If, however, we open up, let's say 4 toll booths at the same time, traffic is going to be able to move faster, right? We split up into 4 lanes instead of 1, and there's a lot less resistance. So we have more current, we have less resistance and more current. So the resistance slows down. Resistance slows down the current that's going through the path. And current is our other thing that we want to bring up, our electric current. And that is signified by the letter I. And I always use the top and the bottom on the capital letter I. We use a lowercase I for other things. And this is universal. So this is an international designation for electric current. So I know I, that doesn't make any sense to you that we're using I, but this is our international conventional acceptance of electric current. It's in all the books. The units of electric current are amperes. And that's often designated with a capital A. So we have units, we have V, ohm, A for amps, and we have different things. We have potential difference, that's our voltage. We have electric current, that's I. And we have resistance. I put resistor here, but we're talking about resistance. And that's a capital R. And we have the units. Now, let's talk a little bit about what is voltage. So, the voltage is the pressure that's pushing something along. Just like the waterfall, you go from high potential energy to low potential energy, there's pressure that's pushing that along. So, it's designated by how much is passing through a certain area in a period of time. So those units are energy per coulomb. How much energy is each coulomb getting that is going through that circuit? The resistance would be volts per amps, and the current would be coulombs per second. Let me see if there are any other symbols here that we really have to get to. I can give you a couple of others for bulbs. So a bulb can be indicated by a loop. So this would be your wire coming to and from the bulb. And this could be the bulb. And sometimes we enclose that in a circle. Oops, I'm sorry. So just a loop, that could be a bulb. And sometimes we enclose it in a circle. That could be a bulb. Other than that, those are really the only ones that we need to know what they are. There are ones for voltmeters and ammeter. A voltmeter is going to, you're going to use to measure voltage. And in the sim that you're doing later in the week, that sim, you'll be using a voltmeter. So this is a multimeter. This can measure voltage, and depending on the settings that you use, it can also measure current. Voltmeter measures the potential difference across the circuit, and current has to flow through. So there's a difference in how you measure it. When you're measuring current, the ammeter needs to become part of the circuit. But when you're measuring voltage, you measure across the circuit because there's a difference between one side of the circuit to the other. So I think that's good for today. I have power also that we can go over. Power is equal to current times voltage. Let me see if I have one more here that I can use. So we'll get rid of Coulomb's law here. I hope everyone did fine with the sim yesterday. I know some people were having difficulty figuring out what to do with that. So power, we use a script P for power. We use a small p for pressure. What else do we use P for? That's not impulse. I don't remember. But we have current times voltage is equal to power. Now, if we don't know current, but we do know resistance, we can go ahead and plug in. Let's see what we get for current when we use this pyramid. So we have power is equal to current times voltage. If we want to know power, we cover up the P, and we have the I for current times the V for voltage. But let's substitute something else for current. So if we want to know current, we divide the power I did not do Ohm's law here. I'm sorry, I'm really off. So we have to do Ohm's law first. So we have voltage is equal to current times resistance. So to find current, we have voltage divided by resistance. So for power, we can substitute voltage divided by resistance, and we bring down the V for voltage. That gives us V squared over R. So this is one way that we can find power. This is another. And yeah, you can do the same thing, substituting I and substituting I and R for V, and you have I squared R. But these are the two that we typically use for power. But Ohm's law, this is an important one. We see that current is inversely proportional to resistance. So if we have our equation, we see that when the resistance goes up, then the current's going to go down, right? When we only have one lane open at the toll booth, our resistance is high and the current has to slow down. So these two are inversely proportional. Current and resistance are inversely proportional when voltage stays the same. And when voltage is directly proportional to the current, and it's also directly proportional to the resistance. So this is our Ohm's law. I'm not planning on us doing calculations with that. If we were in the classroom, we definitely would, but since we're not, I'm not planning on that. But this is the equation that we would use for Ohm's law. And then this is, the other one are the two that we use for power. Okay, so I don't see any questions. Just what have I missed? So Gail, before you showed up, we just went over what's due for the week. I can pull that up again. Today is the quiz. Monday was the PhET lab. And Tuesday was the suggested study guide, important to your learning, but it won't count against you if you don't do it. And then the quiz is today. You need to complete that today, or you do the alternate assignment. The makeup test. Lab on Thursday, and that's Ohm's law. So that's the one that we just finished up. And then extra credit is Friday. And again, you don't get extra credit if you haven't done all of the week's work. So I don't see any questions. You guys take care and have a good rest of the day.